My name is Andrea Oliveri, a PhD student at Eurocom, and today I will present our work, an OS-agnostic approach.
You might have NDSS.
Sorry. Okay, now it's good. Okay. Thank you. Okay, sorry. I'm Andrea Oliveri, PhD student at Eurocom, and today I will present you our work, an OS-agnostic approach to memory forensic. Memory forensic is the art of dump and analyze volatile memory of systems to extract artifacts. Ordinary forensic tools use profiles to extract forensic data from the kernel data structure. A profile is a sort of map which describes the location, the shape, and the link of the kernel data structure, permitting the forensic tool to traverse them and recover artifacts. To create these maps, an analyst must have a deep knowledge of the internal of the operating system. Each operating system and even each release or kernel configuration need a different profile due to the different implementation of the data structure that it uses. In an easy scenario in which an analyst has to analyze a memory dump taken from an ordinary machine like a PC, laptop, or server, which are based on Intel or ARM CPUs, and which run a widespread general purpose operating system like Windows, Linux, or Mac OS that are well supported by forensic tool. And if the analyst has a profile to the specific version of the operating system that is running on the machine, it can use this existing forensic tool to extract information from the memory dump. However, in the general case, if the analyst has a memory dump taken from a generic machine on which can run on very specialized GPUs found, for example, in industrial devices, printers, smartphones, which can use a completely unknown or uncommon operating system as operating system in network devices and IoT ones. And the analyst cannot rehost or instrument the operating system in order to take multiple snapshots and compare them. There are no compatible and available forensic tools to extract the kernel data structure and permit to the analyst to perform a structured data analysis on the forensic data. The profile-based approach is focused on the specific operating system implementation of the kernel data structure. However, data structures are characterized by topological constraints independent from the operating system implementation. For example, for a doubly linked list, the topological constraints are the fact that each node must contain 2 pointers that point to the next node of in a doubly linked list, and a pointer that point to the previous node, and the fact that the distance among these 2 pointers must be constant, and it is decided by the compiler at compile time. The core idea of our work is that it's possible to identify the kernel data structure in a memory dump without any knowledge of the operating system that has generated them, using only topological constraints. To do so, we have as a first step to extract all the kernel pointers from a raw memory dump in an OS-agnostic way. In a previous work, we have demonstrated that for CPU architecture that are based on radix tree, it is possible to extract the kernel address space in an OS-agnostic way using the MMU constraints, essentially the memory management unit. In particular, this is true for GPU architecture like Intel, ARM, and RISC-V. Using the kernel address space as a validator, we test each 4 8-byte blocks contained in the memory dump, collecting the valid pointers. Furthermore, we use a static code analysis tool to extract the global kernel variables that we can optionally use in the next step of the analysis in order to filter out the false positives. To explain the next step of our technique, we use a different implementation of a doubly linked list. As in the previous example, the next pointer in this doubly linked list, n, directly point to the n pointer of the next element of the list. However, the destination of p pointers of the previous pointers are offset by a constant value alpha. This implementation is used, for example, in the Linux kernel. From the point of view of the structural pointer that the doubly linked list, a doubly linked list is composed by two chains of pointers, which represent the data structure skeleton, constrained by the constant distance among each couple of n and p pointers. So starting from the set of all the kernel pointers extracted in the previous step, we construct for a fixed range of alpha values a set of graph obtained referencing all the pointers that we have extracted and adding the alpha value. Each path in this graph can potentially represent part of the skeleton of a true data structure, or can be composed by pointers which casually point each other due to the offset added. For example, here we have a chain of pointers which casually point to the next pointer n2 of the previous double linked list, but does not represent any valid part of a structural skeleton. Imposing the topological constraints, we match chains part of the same data structure skeleton using a hash function derived from a Galois group and filter out these false positive. More details on the matching phase on the paper, because it's very complex. In the next step, we have to determine the size of the nodes in each in a data structure. All the pointers contained in a skeleton of a data structure, here in gray, lies at the same offset in each node of the data structure. This is very important because all the pointers contained because the data located at the constant distance from the structural pointer must have the same type. For example, here in blue must be a pointer. This permits, starting from the skeleton pointer, to extend the size of each node up to including offset containing data that seems to have the same type according to some heuristic on their content, in particular for strings and pointers. To perform the last step of the analysis, we have to introduce the concept of a seed. A seed is a piece of forensic information known a priori by the analyst or easily carved from the memory dump. Examples of seed are a process name, a kernel module name, the IP address of the machine, or a file name. These pieces of information are used as anchor to extract only forensic relevant data structure. Here we have an example using the name of a single process as a seed, in this case the string init. We can filter data structure which point to or contain these strings, and exploring other fields of this at the same offset of the data structure in green, we can retrieve other process names that was running on the machine. We have implemented our technique in a proof of concept tool written in Python called Fossil. Fossil is able to extract linked list, doubly linked list, binary trees, array of pointer to data structures, and to the reference nodes up to one level. Fossil uses strings extracted from the memory dump, ASCII strings, and the UTF-8 strings. We have decided to use strings as seed because they are immediately recognizable by an analyst, and because they are often present in fundamental data structure used in forensic analysis, like the list of processes or list of kernel modules. We have performed some experiment on a dataset composed by memory dumps taken from 14 different operating systems running on a virtual machine equipped with 4 GB of RAM. We have chosen the operating system to run on 3 different CPU architecture: Intel 32, Intel 64 bits, and ARM 64. We have chosen the operating system in order to be as various as possible in terms of the operating system type. We have a general purpose operating system like Linux or Windows, real-time operating system, mobile operating system, and hobbyistic projects. We have, in our dataset, we have operating system with different kernel architecture, hybrid kernel, microkernel, monolithic kernel, real-time kernels, and written in C or C++, and open source or not. We have used Ghidra as a static analysis tool in order to extract the global kernel variable from the memory dump. In a first set of experiment, we want to extract the name of all the processing starting from only 2 of them. Fossil is able to retrieve the true positive data structure for each the operating system with a very few number of false positive data structure. For the majority of the operating system in the dataset, they use linked list and double linked list, linear or circular, to store the information about the process running on the system. However, 2 of them use 2 different types of data structure, and also in this case, Fossil is able to recover them. If we go further and we suppose that the analysts know only one name of a process that is running on the system, Fossil continue to be able to extract the true positive data structure containing the information about the process running on the system. However, the number of false positives is increased due to the increased number of data structure that referring the only seed available. In this case, if we use the global kernel variables as a filtering for data structure that point to filtering from data structure pointed by the global kernel variable, we can drastically reduce the number of false positives for some operating system. In this case, for example, for Linux, but for other operating systems, this technique is not sufficient. We perform a second chunk of experiment in which we want to extract other important forensic data structure used in forensic analysis, the list of the kernel module loaded at runtime, the list of kernel pools, essentially the list of memory areas that the kernel uses to allocate memory for itself and the processes, and the list of file system mounted at runtime. For the majority of the operating system, Fossil is able to recover at least 2 of them, and in particular for some operating system, it's also able to extract a different type of data structure that point to the same forensic data. For example, in Linux, is able to extract the doubly linked list and a binary tree pointing to the structure that contain the information about the kernel module loaded at runtime. This is particularly important because having a multiple path to the same data can increase the probability to detect attacks that tampering kernel data. Furthermore, Fossil is able also to extract other minor data structure that can be very useful during the analysis of a memory dump of an unknown kernel. For example, the list of network devices, the library loaded at runtime, open socket, etc. In the last experiment, we pushed the technique to the limit, assuming a black box scenario in which the analyst does not have any seed at all and want to recover the main data structure that we have discussed in the previous experiment. In this case, we can use some heuristic based on the statistical properties of the pointer and the string contained or pointed by the data structure to filter out and prioritize the data structure identified by the tool in order to facilitate the analyst identification of the real data structure. Because Fossil for each operating system is able to extract 1,000 of data structure. So if you have to check 1,000 of data structure in order to find the true positive, it's very difficult. For the list of processes, for example, Fossil is able to put the true positive list of process data structure in the top 5 results for the 50% of the operating system, and in the top 20 for the 80% of the operating system in our dataset. In conclusion, the OS-agnostic approach based on topological constraints that we have developed permit preliminary analysis in scenarios when the analyst cannot perform a structured survey and goes to supplement existing profile tools without claiming to replace them. It permits to the analyst to start a structured forensic analysis and can be used in all the cases where no forensic tool are available. At the same time, its great flexibility is obtained at the price of very low specificity. Profile-based approach are able to extract data structure containing no seed or data structure based on very customized topology.
Hi, Derek Keith, Lincoln Laboratory. It looks like on your results for the same operating system, just different architecture, you get different results. Can you talk about why that is?
Yes. Essentially, we have used, in particular for Linux, we have used the same distribution for Linux running on Intel and on ARM64. However, the fact is that the same distribution compiled for different architecture may run different processes. So in this, because for the different implementation of the architecture. In this case, if I didn't talk about them, but the result that you see in the table, it's the worst case at all. So in that case, we have taken the name of the process that are more referenced inside all the data structure of the kernel. So that one is the worst case scenario. And the differences are because some process names appears more frequently in one architecture than the other because there are more process with the same name. For example, one of them is systemd. Systemd is used for the process named systemd is have multiple instances and different instances in different architecture due to the number of service that produce in each system.
Very well done. Any other questions? So I have a quick one. You present profile-based versus topology-based as like, two opposing sides. And I have to think there is something sort of in the middle. So there was this line of research number of years ago now, I guess, that used binary analysis to sort of extract, it was like type inference, basically, to extract fields of data structures, like constraints on integers, constraints on pointers, constraints on characters. I'm curious, what's the trade-off between like sort of a type inference approach to get data structure signatures versus this topology approach to get data structure signatures?
Okay. I think that the use of code analysis in order to infer from the kernel address space, in particular for the kernel code, from the kernel code, it can increase drastically the resolution of fossil in this case, because we can infer also the type of the data in the data structure. In our proof of concept, we are only able to infer pointers and strings, and also some particular int values as a PID or timestamp, because they are very easy to identify. But if we can use the code analysis inside the fossil, we can extract also we can extract more type of data that without any knowledge of the operating system. So yes, it's a good idea, and yes,
cool. Let's put them together.